All right, so the first derivative, this is a little review in here, highlight this for yourself. The first derivative tells us many things, okay? It tells us our extrema, our maxes and mins, and whether they're increasing or decreasing. Okay, so we've spent all last week, this week, we've only been talking about the first derivative. Okay, and you have to set it equal to 0, and then you always have to make a sign chart to answer those questions. Now, the second derivative, that's where we're headed today. The second derivative can help us understand a lot of features here, and it's going to lean towards concavity, concave up and concave down, and points of inflection. All right, so what do we mean by concave up and concave down? So let's kind of draw a picture here. Concave up. Okay, so if a function is concave up, means it can hold water. So something like this. Something that can hold something. Okay, we call this concave up. We talk a lot about this in algebra too when we start drawing like the sine curve. We would talk about whether the function was concave up or concave down. We'll abbreviate that as CCU, and that's fair game on the exam, concave up. Concave down, okay, is the opposite here, like a negative x squared function. And again, we'll call that CCD. You can abbreviate that the whole exam, that's fine. Concave down. Okay, so if I want to talk about concavity, this is all about the second derivative. Okay, so increasing, decreasing, max, min, that's all the first derivative. The second derivative, which we're introducing today, is about being concave up, concave down, or what we call a point of inflection. And you can abbreviate that a POI if you want, a point of inflection. Okay, and a point of inflection is where the concavity changes. Okay, so for example, if I draw the sine curve, okay, it starts off concave down, and then someplace in here it switches to concave up. Right where it changed from being concave down to concave up, we call that a point of inflection. Okay, so anytime my concavity changes, it's a point of inflection. And again, this is all about the second derivative. We can find it. I'll show you in a few minutes how we'll find it. So this chart is just breaking down who uses the first derivative versus the second derivative. So if you want to, so here's f prime, bless you. F prime, if you're looking for a critical point, increasing, decreasing, max, min, all of those are saying first derivative. And then again, you have to make a sign chart. This happens every year. There is one person, and it's always one person, who will take this test and they don't make a single sign chart and they get every question wrong. Every time you're saying max, min, increasing, decreasing, you need a sign chart. You can't answer the question without it. The second derivative is going to talk about concave up, concave down, and points of inflection. Okay, so you're setting the second derivative equal to 0 and making a sign chart. Let's try to break the streak this year. See if everyone can make sign charts. Okay? All these questions need sign charts. It's just whether you need the first derivative or second derivative. All right, flip the page. So let's start with example 1 here. Find the open intervals where f is concave up, concave down, and any value where there could be a point of inflection. The 0 to 2 pi I think is supposed to be on the next problem. Cross that off. There's no trig involved here. Okay, so your brain's got to say concave up, concave down, point of inflection. That's all second derivative. Now you can't get to the second derivative without taking the first. So take a moment to get the first derivative. So I've got, what is that, 4x cubed minus 6x squared minus 24x. Then I need to take the second derivative. So I'm going to derive it. So I've got oh, tree. I'm going to derive the first derivative. Zip it, Luke. Minus 24. All right, now before I attempt to factor the second derivative, what do you notice that hopefully? There's a GCF. Make your life easier. We can pull out a 12. Now don't lose the 12. It's still part of the problem. Okay, so now I'm setting that second derivative equal to 0. Keep the 12. My only factors of 2 are 2 and 1. So x minus 2, x plus 1. Okay. Remember, I'm going to tee it up between all my multiplication. How many x's are there? 2. So there should only be 2 possible points of inflections here. So I get x equals negative 1, x equals 2. There's no x to solve here. 12 equals 0 doesn't make any sense, so there's only 2 values here. Now again, I'm going to highlight this one where I set it equal to 0. This is where I'm plugging everything back into. Okay, so I'm making a sign chart. Now the only difference is where did we get these points from? Which derivative? Second. So you're labeling this the second derivative. Those points came from the second derivative. Okay, now it's not a point of inflection unless the signs change. So you can't just circle negative 1 and 2 right off the bat. You have to make the sign chart to see if they actually change. So if I plug in a 3, I have 12, which is always positive. 3 minus 2 is a positive, and 3 plus 1 is a positive, and 3 positives make a positive. Now what I put underneath, remember this is the second derivative, so I'm going to show the concavity. That means this is concave up. Between negative 1 and 2, who's a safe number to pick? 0. So 12 is positive. 0 minus 2 is a negative, and 0 plus 1 is a positive. So that's going to make a negative, so that's concave down. And if I plug in a negative 2, so 12 is positive. Negative 2 minus 2 is a negative. Negative 2 plus 1 is a negative, so this is going to make a positive. Okay, so now we have a bunch of information we're going to identify here. So we're going to talk about first being concave up. Okay, so I'm concave up where my second derivative is positive, so from negative infinity to negative 1, and from 2 to infinity. And my justification is because the second derivative, f double prime, is greater than 0. I'm concave down from negative 1 to 2, and my reasoning is the second derivative, f double prime, is less than 0.
So are we not using brackets anymore?
Correct. So increasing, decreasing is a bracket 100% of the time. The rest of this is going to be parentheses. Good question, Mace. Now, points of inflection. Okay, to be a point of inflection, f double prime must change signs. Okay. Now again, you can't say something changes signs if you didn't make a sign chart. So just keep that in the back of your mind. So I changed signs at negative 1 and at 2, so both of them happen to be points of inflection. But again, all of these questions need sign charts. Okay, so first derivative is going to answer increasing, decreasing, max, min. Second derivative, concave up, concave down, points of inflection. Dree, you look like you have a burning question.
I do, and I have for a hot minute.
Oh dear. Buckle up, everyone.
How exactly, like on the graph of the original equation, does the second derivative show us concave up or concave
So
down?
at negative 1 and 2, so if I graph, so at negative 1 and 2, now I don't have like my increasing, decreasing plotted out, but at negative 1 and 2, this is changing from concave up. So at negative 1, it's going from concave up to concave down. So I'd have to find the exact value, but it's concave up, so it's going like this, and then it's changing to concave. That's not looking right. At negative 1. So I'm changing from concave up, so maybe like this, and then to concave down. So at negative 1, I've changed from concave up to concave down. And then at 2, I was changing from concave down to concave up. We'll shift that point over a little. But it's kind of that magical point where you can see that it's turning from one direction to the other.
How does it get to that? Like, if we were to take the derivative, what would that derivative look like so that we
So
know?
we'll get there eventually. We're just going through, we will get there. You actually have to draw it all out yourself. That's coming in a couple days.
Like, I'm trying to figure out mentally, like, how
Yeah.
to get
You're just
from
like
that
3 days ahead of us.
to that.
It's coming, I promise. All right, example 2. Find on the open interval, I think this is where that 0 to 2 pi was supposed to be. Let's add 0 to 2 pi because trig needs an endpoint. Where g of x is concave up, concave down, and any points of inflection. Okay, so I'm specifically picking a trig since that seems to be part of our weaknesses here. So notice, who did they already give you? So how many derivatives do you have to take? 1, because you only need g double prime. So a lot of times, be cautious on who they give you. You just need g double prime. Just take 1 derivative. And be careful. That is the repeated chain. This is really the sine of x all squared. That is a chain rule. So who comes down in front? Keep the inside times the derivative of the inside, which is cosine, and then minus sine of x. Okay, this repeated chain is on every Monday quiz for a reason. It pops up in everything. Rewrite it for yourself. Bring down the outside, keep the inside, derivative of the inside. All right, so I'm setting my second derivative equal to 0. What should I be looking for next? What do you notice they have? GCF. I can pull out a sine, and then I'm left with 2 cos x minus 1. Okay, these are factors, right? It says times. Any place I have a times, I have factors. Okay, so I'm going to set sine of x equal to 0. So when we set a function equal to 0, hopefully you're picturing the graph. How many times does sine equal 0? 3 at 0, pi, and 2 pi. So again, I'm just picturing the sine function. It hit 0 3 times. Okay, those are the easy ones when it hits zeros and ones and negative ones. These are the annoying ones. So I've got to solve for cosine of x. Who am I going to move over first? The 1, and then divide by 2. Okay, so here's where all the self-taught comes in. When I'm in a quadrant, you have to remember you're always in 2 quadrants. So all students tip cows. Cosine is a what type of number based off this? Positive. Which 2 quadrants could I be in? 1 and 4. Perfect. So I know I need my 2 answers in 1 and 4. So now I have to think of my reference angle. Is it 30, 60, or 45? 60. So 60 is in degrees, which is pi over 3. Okay, so now I need an angle of pi over 3 in quadrant 1 and quadrant 4. Quadrant 1 just is what it is. That's pi over 3. Okay, so we kind of talked about a little trick to keep things in radians. So if I have to come back to quadrant 4, I'm going to be 1 away from here. If my denominator's 3, how am I going to write 2 pi? 6 pi over 3. That makes this one 5 pi over 3.
That doesn't quite match up because 8 pi over 3 isn't the same as pi over 3. Sorry,
It would be 7 pi over 3. It is.
How is it the same as 2 pi over 3?
I'll talk about that later, Dre, but it is. I got to keep going with this just because we have a lot to get through today. So I've got 0. I got to put them in order. Pi over 3. 5 pi over 3. Oops, I missed pi. Sorry, pi. 5 pi over 3. And 2 pi. Okay, so pi over 3 is in quadrant 1. Pi was here. 5 pi over 3 is here. And then 2 pi is where it ends. Okay, so again, I'm plugging these into the second derivative because we're talking about concavity. Okay, so let's think about this. Between 0 and pi over 3. What do I know about sign in this quadrant? Positive or negative? I don't care what the number is. Positive. So I have a positive times. Now I have to get a little creative here, right? This is 60 degrees, right? So I need the cosine. Now I have to do a little math here because I have to subtract 1. So this one's a little more intimidating because I have to, crunch some numbers actually. Who can I pick before 60 that I know? It's a trig angle we know before 60. 45 or 30. I'm going to go with 30. What's the cosine of 30? Okay, so I have 2 times root 3 over 2 minus 1. Now think about this. What happens to my 2's? They cancel. All I need to know is root 3 bigger than 1 or smaller than 1? Bigger than 1. So this is going to be a what type of number? Positive. So I'm going to get a positive times a positive, which is a positive, which tells me this is concave up. Okay, now I need someone between pi over 3, which is here, and pi. Who's a really smart number to pick between those two? Pi over 2, because I can just look at the curve, right? What's the sine of pi over 2? Positive 1. What's the cosine of pi over 2? Picture the cosine curve. 0. So 2 times 0 is 0. Minus 1 is a negative. Therefore, this is going to be a negative, and this is concave down. Okay, so again, look between pi and 5 pi over 3. Who's a smart number to pick? 3 pi over 2, because it's on the curve. The sine of 3 pi over 2 is a negative. The cosine of 3 pi over 2 is 0. So that's 0 minus 1 is a negative. The two negatives make a positive. Okay, so now again, I need somebody between, this is 60 away. So if this is 60 away, who's somebody between those two? Somebody that's what away? 30 away. So I'm using 30 as my reference angle. So the sine of 30 is definitely a positive, right? It's in the first quadrant. The cosine of 30 is cosine of 30? Root 3 over 2, and it's in the fourth quadrant, so it's a positive, so that's root 3. Same thing here. Minus 1 is going to be a positive. Okay, and then I can identify where I'm concave up, concave down, and any points of inflection. All right, so I totally get the trig is annoying. Luckily, there's not a million of those, but we're just going to keep doing 1 or so a day here. All right, flip the page to number 3. Now, you've got to be really careful who you're staring at when you answer these questions. The graph of f prime. So you are staring at the what derivative? First derivative. Find the intervals where you're concave up and concave down and any points of inflection. So the first thing I do is justify. If I'm let's start with concave up. I'm talking about who? F double prime is what? Greater than 0. Okay, now you got to be smart. This is f prime, and you want to say f double prime. What are you looking at? The slopes. Where do we have positive slopes? From where to where? Negative infinity until 1. These slopes are all positive till I get right to here, which is at 1. Concave down. Again, start with justifying. F double prime is less than 0. Again, I have f prime. I want f double prime. I'm looking at the slopes. My slopes are negative from 1 to infinity. Point of inflection. And again, I always start with the justifying. F double prime changes signs. So again, I'm saying to myself, this is f prime. I want f double prime. I'm looking at the slopes. My slope went from a positive to a negative, so x equals 1 must be a point of inflection. No. The critical points you do.
Or which, if it goes from negative to positive or positive to negative?
Nope. This is perfect. All right, example 4. F double prime equals this. Find any values where there is a point of inflection. So kind of highlight the calculus word for yourself, point of inflection. And now your brain's got to say, who are we looking at? F double prime has to change signs. I am going to say F double prime equals 0 and changes signs. Now, who did they already give you? They're trying to be helpful. They gave you F double prime, so go find your critical points. Do those exponents matter? Not at all. I should get x equals -2 and x equals 1. Can I say those are points of inflection? Everyone say not yet. No, you have to make a sign chart. Take a minute and we'll see if we get the same thing. They're going back into F double prime. Excuse me. All right, let's compare. -3. What's -3 plus 2 is what type of number? Negative. And if I cube a negative, I still get a negative. I don't even care what I plug in here. I'm squaring it. What's it always going to turn out to be? Positive. So this is going to get me a negative. So I'm concave down. If I plug in a 0, 0 plus 2 is a positive, and 2 cubed is also a positive. Again, I'm squaring this. Anytime I square it, it's going to turn out to be a positive. So this is a positive and concave up. If I plug in a 2, 2 plus 2 is 4, cubed is a positive, and I'm always squaring this, so it's always a positive. Where do I have a point of inflection? Good. X equals -2 is a point of inflection, and my reasoning is F double prime changes signs. Yep. So something that is concave up, and then I got to stay concave up. Hold on. Something like this, where it's non-differentiable, is one example, where I'm concave up. I come to my derivative doesn't exist, and then I go concave up again. So something that, has something like derivative like that. All right, H. The exam loves this question. It's over and over and over. Well, on the ones they released anyway. All right, the graph of H prime. So you're staring at the what derivative? First. On what open intervals is H of X decreasing and concave up? So when they say decreasing, your brain is saying, look at who? H prime of X. When we hear decreasing, who are we looking at? I'm sorry, when we hear concave up? H double prime. So you got to be thinking two things. I need to be decreasing, so H prime has to be what to 0? Less than 0. And if I'm concave up, H double prime has to be greater than 0. So I've got two things cooking at the same time here. Okay, I have to be decreasing and concave up. So let's start with decreasing. And again, if you write your justifying down, this is usually very easy. If I am decreasing, H prime has to be less than 0. Now you happen to be staring at H prime. So where are you just looking? You are looking below here. This is where h prime is less than 0. Up here is where h prime is greater than 0. So my answer has to fall in my box. Would you agree with that? This is where h prime is less than 0. Now looking in this box, I need h double prime to be greater than 0. So now I'm looking at the what down here? The slopes. I need the slope to be greater than 0. Give me an interval in this box where the slope is greater than 0. 2 to 5 is a great answer. Any other time? 8 to 9. Okay, and my reasoning, again, is h prime is less than 0 and h double prime is greater than 0. So if it matches h prime, I'm just looking to see if it's sitting above or below. But if I want to take its derivative, I'm looking at the slope. Does that make sense? So be really careful on that, what you're looking at. Let's see. Let's try to put it all together on one of these. All right, the graph above is f prime. Okay, so we're given f prime. So we're staring at the first derivative. Go get A, B, C, and D. And justify. Mason, number 1. Where are we increasing? What's your reasoning first?
It has to be greater than 0.
What did you just say?
F prime has to be greater than 0.
All right. Guys, everybody owed me when I said it. We only gave him 1 O. F prime is greater than 0. And what's your interval?
From -1 to 7.
Yes, and shoot, increasing, decreasing are brackets. -1 to 7. Yeah, so increasing, decreasing are brackets. That is beautiful. Mason, number 2, justify decreasing.
F prime of x is less than 0.
Beautiful. Give me your intervals.
-2, -1, and 7 to 8.
Yes. And the reason we're stopping that is the closed interval was -2 to 8, so just don't use infinities. It said between those two values. Joey, when do you have a relative min? Give me a justification first.
When f prime of x changes signs from negative to positive.
Yes, I'm going to add one thing in there. F prime has to equal 0. And then F prime changes signs from negative to positive, you said. What value did that happen at? Perfect. Okay, so the derivative has to equal 0. We have to say it's a critical point first, and then f prime changes from negative to positive. For relative max, likewise, f prime has to equal 0, and this time f prime changes from positive to negative. Where would we say that value is? Good, x equals 7. Okay, so all 4 of those questions were about the first derivative. Now we have concave up, concave down, point of inflection. Now we're looking at the what derivative? Second. And if this is f prime, you are now looking at the what of the graph? Slope. All right, so give yourself another minute and try to answer E, F, and G. love it. All right, Anna, justify concave up. Perfect. F double prime is greater than 0. And what's your interval here? -2 to 3 is perfect. So we're saying when the slope is positive. Great. Concave down. Leo, what's your justification? Perfect. And your interval? Perfect. Okay, so again, we're just looking at the slope. Point of inflection is when F double prime changes signs. So again, I'm looking at the slope. I changed from a positive slope to a negative slope at x equals 3. All right, grab your 3 flashcards. We're going to go concave up, concave down, point of inflection on the front of the 3 of them. I think they're all getting replaced.
It won't be so slow anymore?
Hopefully, I can't guarantee that. All right, what do we got? Concave up. Okay, our reasoning is F double prime is greater than 0. And again, I'm going to make a note. You need a sign chart. Okay, unless you're looking at the graph. All right, if it's an algebraic equation, you have to make a sign chart. Concave down. Concave down. F double prime is less than 0. And again, you need a sign chart. Point of inflection. So I'm setting that second derivative equal to 0, or I can say it does not exist. It could come to a sharp corner or cusp. Okay, so again, you're setting that second derivative equal to 0, and then F double prime changes signs. And again, if this is algebraically, we need a sign chart. If it's graphically, you can just look and tell. But if it's algebraically, you got to have a sign chart. And lastly, tonight's homework, flip to page 213. Okay. Now, again, be really careful. Some of these already are the second derivative. Some are the original. Some are the first. We're going to go 1, 2, 3, 4. You don't want the trig? It's already the second derivative. I think we should do it for fun. 5. It's already the second derivative. You just got practice. And then on the back side, these are quick, 9 and 10, and I think they're super quick. Okay. So 1 through 5 on the front, 9 and 10 on the back. Test Friday.